resiliency, even though some of these that I'm going to talk today is also applicable for resiliency against weather event. So just to start, so here is something that I'm sure that some of you already have been in the power grid control center. It's a very high stake job for the operators. And typically if nothing is happening in the grid, which is rare, they don't need to do much, just do what is planned and keep observing. If something is happening, like a weather event, they are in a kind of stress scenario and they have to take decision and also get approval from supervisor several times. If something like a cyber event is happening, that's much more stressful because they are not aware anything about it. Any cyber attack or any cyber event that will happen, typically it's not known to them. And we know that there are two different control center. One is a power grid control center, which is this slide is showing. And the other one is network operation center, where you observe the cyber information. There are a few utility who are trying to integrate those two data together. And more and more information from the cyber is being informed to the operator. But if you think about it, we already have so much of data. And if you bring the cyber, the challenge is that how do we combine or integrate these together to provide ability for the operator to make a decision and also in time, right? So in another, just to summarize that control center operator are in high stake scenario where their job is very difficult and challenging, especially if something is happening. So if you look at especially news these days, from last 4 or 5 years, these attacks have been more and more increasing, right? And there are several, news articles. These are just some example which resulted into impact, right? And the Ukraine attack is one of the, you know, closest example that happened twice in 15 and 16. So what it results in that they don't know anything about what's happening to the grid, but in their console, they start seeing a bunch of these, alarms, and they need to start responding to this very soon, right? Before the spread is kind of spreading in that any cyber attack is spreading into the network. And this is not possible by a human grid operator. So uh, first, they're not trained for these extreme event when it happens. So, we do some planning, we do some analysis, but the cyber data and all the extreme event, we never train them for. And of course, it results into consulting with each other, trying to figure out what's happening, and discussing about what to do. So then the question becomes what we can do about it. Now, of course, we do need to train, and we need a support team, which will be a cyber physical or cyber power expert, and of course, cyber expert and power expert to do that. And if for some reason, which is one of the worst kind of a cyber attack, like Aurora attack, which can result into physical system damage, then we need a crew to repair it. But the most important thing is tools, because a human operator cannot process all these information in short time. We always, as we in 1965, when we went towards more and more computerization, we have been developing a lot of tools. Now with this new set of data, what kind of tools we need, right? So we need a tool for alarm processing, which we already have in some way for the power. Now we need alarm processing for the cyber power. We need anomaly detection. We need to process those. We need to rank them so that operator can really take action for those anomaly, which may result into a outage or which may result into any kind of damage to the grid. and also find the root cause, because without finding a root cause, we cannot help operator much that what to do, right? And turns out it's not an easy job, right? So this is what I'm going to focus on today, not on the other two, which is training and supporting. Now, once you talk about these advanced tools, then you look at all the data that we can have from anything that we can get from relay, from PMUs, from SCADA, from cyber system protection, and all these data will be coming to the control center or to the substation where we can process it. And like I said, that the first thing we want to do is to process and find, is it anomaly or it's a normal? Again, that's not an easy job to do because our system is dynamic. It's a dynamic system. And once we find an anomaly, we need to classify it, what kind of anomaly it is. And then after, we need to do the kind of root cause analytics. And that need to be done from both sides. We all know that we can use our algebraic and differential equation and kind of do the dynamic state estimation, but those will most probably will not work in extreme event. And the reason is obvious, that you don't have a data to trust. And we know that state estimation kind of algorithm will not work very well if a certain percentage of data has anomalies. Now, even the machine learning algorithm will not work, because if you have more than 50% data bad, most of the machine learning will not work. But some will work. And that's what we'll talk about and focus on. And then we need to visualize those data to the operator so that they can make a decision and they can think about that what to do, right? Now, with this all set of data and tools that we need, then it becomes that how much you trust. Do you trust your still state estimation, because we can get a number out of state estimation which will tell that how good we estimated. And same thing we can do from data driven and machine learning approaches or AI driven approaches, to also report that how much trust you have on this. So not only we need to detect anomaly, but we also need to detect that we are doing it with certain trust or percentage confidence. And also, when we are doing it, we need to monitor the resiliency. We need to change it to some kind of number, which, just like reliability is being monitored, we also need to do the resiliency. Stability is being monitored. And if this is going down, we need to first figure out that it's going down because of cyber or because of physical, and then take an action on that. And all these tools will help in doing that. Other big factor is human operator. They're the one who are looking at these window and making a decision. And we need to keep in mind their human brain or cognitive ability to take action. And if you talk to cognitive scientists, then they tell that if nothing is happening, they get bored and their ability to perform well is less. And if a lot of things are happening and they're stressed, then again their ability to perform is less. So we have to find this process that where they perform best, and this will be different for each different human operator, and that depends on cognitive flexibility. And we can measure it with their some kind of galvanic skin response, some kind of eye tracking, and then the other thing like operation span, backward digit span. So this is all the work is being done by my collaborator in cognitive science. And then on these two, if we do these kind of things and we know ability of each operator to perform under stress, then sometime we need to question: do you trust a human operator, or do you trust these tools? And then you need to do the adaptive data fusion and decision making process. Now I'm going to focus on this part. And basically I once I focus on the tool, then I'm going to talk about four things. One is How do we provide situational awareness and decision support in the control room? Using two tools. One is synchrophaser anomaly event and detection and classification, sync ADC. And the second one is CP-TRAM. How do we validate in control room environment? And that's where the cyber power interdependence modeling and simulation comes. And then third, show some results and use cases by modeling, and then finally summarize it, right? So let's talk about the first one. And these two tools are Sync AEDC and CPTRAM, which we developed here. And I'll talk about both of these a little bit more. So first one is that, which relates to anomaly detection. We do have a data from PMU. You do have data from SCADA. You can also program your relay to provide you more data. And all of these, interest of time, we cannot talk, but I'll focus on just the synchrophaser. And then, I'll refer to some of the papers which integrate SCADA and relay information with the PMU to make a decision. So once we detect an anomaly, we need to classify it. We need to find the root cause and then rank them. So operator can focus on the most critical one, right? And then again, we already talked about that we need to monitor those with the proper visualization, considering the human cognitive limits. And then these two things are more important. Sometime we need to take a proactive control even before things happen. In cyber event, it is very difficult, but once we detect it, you can take a proactive control in unaffected part, which is, assuming that, whatever you know and have learned anomalies is the only one, right? So sometimes proactive control and sometimes remedial action need to be taken. And these tools should tell you. So the problem that we have, you have SCADA data and communication network data and PMU data, everything is coming to you. And you're looking at two set of data. One is physical data, which is, again, CTPT measurement, PMU, which is part of SCADA, breaker state is part of SCADA, relay operation. And then cyber data, which is network data, which will tell you the traffic, network flows, and then some IDS alert. Also, you can get data from host, event log, IDS alert from there too. And then what we're trying to do is detect anomaly and classify it, localize it where it is, and again, classify the event. So once you know that it's not a bad data, it's not an event, and those event could be anything. It could be a physical fault, which is normally expected or normally not expected. It could be a device malfunction. It could be cyber attack. It could be cyber physical. A lot of possibilities there. And then correlate it and prioritize it, and again, give it to the operator, and combine that into a number where the resilience is being monitored. And these two, this part and this whole part is kind of interrelated. By using this set of data, you're processing that to a number, which is cyber resilience metric, and then you're trying to monitor that, and then root cause is happening through all this process, right? And then sometime you do the prognosis. Of course, we already have short-term planning and proactive action, at least short-term planning and proactive action can be embedded into that. So first, let's look about sync ADC, which is synchrophaser anomaly event detection and classification. What can go wrong? And it turns out there are a lot. So if you look at first that we want to differentiate between two things. So if you need to classify, one is data anomaly, which is typically does not have any spatial temporal correlation. And other one is event anomaly, which does have a spatial temporal correlation because it follows the physics, right? So one which does not follow physics, one which follows the physics. Now, if you go down on this, of course, the noise and uncorrelated bad data will be there. But there are some data which is related because the way the synchrophaser data flows from one location to another location. And that will be, PMU and PDC connection. So if you see something anomaly in PDC, maybe it's a cyber problem, and PDC is showing that problem because of buffer overflow or GPS is not correct. So there are some correlation in terms of cyber network, and then you get to the cyber related, GPS spoofing or mesh data. So just given, and then I think you can go through this also, but there are some control problem. There are some disturbance which is happening unexpected and some expected. Physical system, which is like a fault. And these are some only examples. So these are not, of course, complete list. And all these different anomalies are being observed in the physical system or sensor layer. So your CT and PT could be wrong, and that's why PMU is, it has a bias. And so PMU is not giving you correct result. And at the network layer, which is the cyber layer, and then application layer. So a lot of these possibilities need to be differentiated, and we need to get to the root cause as soon as possible, as soon as we see it. So to start that process, almost 6 years back, we looked at, okay, let's look at simple, uh, some data analytics approaches and compute that can we find anomalies. So here, as you see, there is no single method which can identify all the anomalies in single feature data, right? We tried with Chebyshev, linear regression, DB-scan. These are all three different kind. One is clustering, one is regression, and Chebyshev is also kind of regression. So there's no single winner, which means that we cannot find a base detector which will work in all the different conditions. And this is a very small example. Of course, we worked with the whole vec data and several thousands PMUs. The other thing that we look at, that all these simple approaches require some tuning. You need to tell in DB-scan that what is the radius that I should put the new set of data. In regression, you need to tell that, okay, what is the outline I'm looking at? And Chebyshev, you get more flexibility to set two different, kind of limits to look at, and which can adjust in different window. But all of these require some tuning. And the more important is that we don't have a training data, right? And even if we have a data, we have not labeled it, what is anomaly, what is not, right? So when we went with the whole VEC effort, it was very challenging because any anomaly you see, you need to discuss and call the engineer and look at all the other file that what happened to confirm that it was anomaly or not, right? Is there any physics-based event that happened? So training data is very less. Okay. So what we came up with that, okay, one technique is not going to work. So let's integrate it and make an ensemble-based technique where you can, not too much dependent on one approach, and also there's not much parameter tuning is required because you're going to scale it while combining and integrating. And also it's unsupervised, which means that if you don't have a training data, it's okay. We can use the training unsupervised, even though I'll show you some result with some supervised method also we used, where you don't need a lot of training data because it's called soft leveling, where you put in terms of percentage, that's a very new research, soft leveling the data so that you can minimize the number of training data needed. So in this whole process, and the details are in more papers, but what we do that we take a data and then we apply these base detector. These are three listed. You can add more and more. Like for example, we applied LSTM, we applied random forest, and we apply RNN, we apply CNN. So all these and GNN, graph neural network, is the most recent paper that we had this year. So we apply a bunch of different base detector. We get some outlier score, which is kind of a confidence that you have that this is outlier or not. And then we normalize it, and then we integrate it using MLE to make an ensemble. And then finally, we look at some approaches like as simple as Prony to unflag anomalies or divide the anomalies into event and bad data, right? Because if it follows the physics, then Prony will be able to detect that. That this is a physics-based event. It's not a bad data coming from the sensor or coming from something else. So finally, we can do a classification of bad data versus event, and also at the same time we can think about that, should we replace it or should we flag it, right? And the next part becomes, now we know that what is event, so we flag or replace the bad data, we took it out, and then rest of the data with the same window, we process it and we classify it. So in classification, I'm first trying to do it the broader level. That's this active power, is it active power, this is a fault event, or it's an unknown event. And unknown event, of course, requires some more analysis, but these are three most common one. And then further classify it based on the graph of the system network from the physical. We can also do the cyber, which is not shown here, but we can do the cyber network, which is done in another paper. And then we use the whole graph and find out that it's kind of zooming in and saying that, okay, this PMU has showing the most in neighborhood, is slowly in the near area, is not showing that much anomaly, because we are measuring that how much anomaly we are seeing it. And that means that you, just like a GPS triangulation, you can also apply here graph triangulation, and you can find out one or two different key point or PMUs where there is a anomaly. Of course, you don't have a PMU enough in the system, so you need to look at other kind of scan data to further. So PMU will give you the area where the problem is in terms of classification, and then you need to use the other set of data to localize the event. And sometime you need to make an iteration through here. Once you localize, then you can go back, then does it agree with broader classification, right? So localization and classification might make us some loop. And then finally what you get is detection, classification, localization, and then you go back to the get the new data window, and sometime it will be a adaptive data window. You have to extend it, which is the one thing that we did like almost 2-3 years before that. You have to extend the window to look at a small and then a larger time window and make sure that it's showing the same thing. If it's not showing the same thing, that you need to experiment more. That's adaptive window processing. So this part, where we see the event through PMU, we use cell entropy and crest factor to normalize the score, which is just statistical approaches, to zero down that where is the problem. And then we came up with another, technique, knowing that anomaly definition is changing. So because power grid is a dynamic system, and if one line goes out, what were the anomaly, definition you had, that's not applicable anymore. And this is called a concept drift or data drift in machine learning approaches. So now we have to pre-process data and detect that, SCADA is saying that, okay, one line went out or something happened. And if it is being reported, then we quickly move to a different definition of data. And then we apply this dynamic data change driven learning, which is DCDL. And the other one is a continuity driven learning. As the name says, then we will continue to learn in CDL, while DCDL, it's a dynamic data change driven. And then finally, we'll go through the same process. We'll still normalize all the data and finally able to detect. This one was done with GNN, which is a graph neural network in this case. And that's why it's the most recent paper. So now you got data from PMU, you got data from SCADA, and then we look at the streaming cyber data, which is typically from IDS or traffic data. And we can process all of these. So I'm not going into detail, but this one I just talked about. We also applied autoencoder in the past, which is another paper, but this could be a whole ensemble approach. And then some key things is coming here once you to localize further. And then cyber data will be used to find the correlation. So if you see something in cyber and in the physical system, then of course it's cyber physical. If you see something in cyber, an impact on the power, but no anomaly in the power, then it's a cyber event. And if you see something only in the physical, but nothing, no anomaly in the cyber data, then it's a physical event, right? So it's easier said compared to how challenging it is. The final goal is that once we see something in the control center, then again prioritize it so that operator can focus on the top one, which is going to impact your grid most. And that's where the resiliency comes. So this resilience monitoring part will be added, and I'll talk next about this, where resilience is defined as ability of our grid to supply power to all critical load. Of course, that's a connected and distributed system, so that relates to a substation, a specific substation that we want to focus. And we are looking against a different kind of event, right? So here it's a cyber. So that tool is called CPTRAM, and the more information is here in this paper. So CPTRAM looks at all the physical factors which can tell me ability of my system to keep supplying critical load. And those physical factors, could be anything from the network architecture to the control and to the resources. And resources means that all the megawatt availability, and then, of course, the one thing that we're looking is the loss of critical load. We take these factors, which is impacting my resiliency, uh, put some weights, combine that with the multi-credit decision-making process, which is here AHP, analytical process, and then we get the physical resiliency score. Same thing we do with the cyber factors, which will again look at the network, which will look at the different kind of the communication topology if you're trying to plan something, or it will look at attack graph if you're trying to look in operational, and look at all the different factors that we can measure, which is, of course, the communication data packet, traffic, and bandwidth, and all those things we can, again, put as a factors and combine that with certain weight using this AHP. So if you look at typically resiliency metric, one are performance based and one are system characteristic based. So this this metric is system characteristic based, which is very similar to stability, not reliability, because reliability is a performance based metric. Well, stability is a system characteristic based metric. So ours is a system characteristic based metric. And then we can combine these to report cyber physical resiliency. And as soon as something goes wrong, we can look back. So the advantage here is that you can always trace back the root cause because we are combining the factors. So we can look at here and then find out that, okay, the cyber is going wrong or physical. If cyber is going wrong, then which factors caused it? So we can always trace back, and it will help in root cause faster than if you look at performance-based metric, which does not tell anything about the why it's happening, the system level information. Now, once we have this, again, the detail is in the paper, so I'm not going into detail of this equation, but here are just example of different factors that was, integrated together. So, speedy index, megawatt availability index, megawatt availability index, all these are computed. And then finally, we get into how we want to use it. So for example, this is again a very simple example to compare. If you have a different security mechanism for authentication, monitoring, access control, data encryption, attack knowledge base, preparedness for the cyber attack, and like educational plan, and we can give some number in terms of low, medium, and high based on the way you do it. So for example, authentication could be multi-factor or could be role-based. And based on these, I can compare that what to implement in the most economic manner, which still gives me enough resiliency, right? So if I want to compare education, how much investment I can do, and then I can compare that what kind of security mechanism I can apply, I can find out the resiliency for both, and I can tell that, okay, what you should do. Now, again, like I said, that's very simple, but I can add more and more ways of doing that, and then I can compare those things. So given that we can use it, so let's talk about next part, which is how do I validate, and with and setting up a kind of some test bed, which is cyber power interdependence modeling, which should add multiple different things. So these are the two test bed we have, in WSU. So this is our control center, which is running with GE, EMS, DMS, MEMS, and also with INCSys power simulator, training simulator. And then we have OPLRT, we have RTDS, and we have a bunch of PMUs and relays and PDC and, of course, GPS. We also have micro PMUs. So all these are connected together, and these, as you can see that these are different kind of PMUs, so 6 different kind of PMUs. But we can also model PMUs in the simulator, several of those, in fact, other than this physical hardware in the loop. So then what we want is to model the physical system, to model the cyber system, to model the cyber attack system, and to model the control room environment. So we are using OpenRT in this case so that we can do the real-time simulation for dynamic. Then also, if you, I think some of you already know that in EMS, we do not do the dynamic simulation, right? But so if you look at the training simulator, it does not do a dynamic simulation, neither the cyber part. So we need to add those things and somehow put new window, which will look at cyber data and the dynamic information which is coming from here. So there are a lot of partners in this project. For example, you see, we already talked about INCSys EMS, which is training simulator, and we can basically divide into a different part. Pingting, which is known as a historian and data processing for PMA data, and SCADA we have from several vendors. We also have a partner called Resilient Grid, which visualization look like this. And we'll talk about a little bit more about that. The other thing important is that it should allow us to model different cyber attacks, right? So it should be a physical router, physical switch, and all those kind of things. So I can do that. And to do that, here's a little bit more detail showing that how it's layered up. So again, you have a substation network, which is being modeled in HyperSim and a complete system. And we are modeling a Washington State system, which we call Cascadia system. Then we have a bunch of relays and PMUs and everything. And then NS3 is being used here as for cyber simulation, which is integrated and can be kind of interfaced in real time. Then we are modeling some hardware switch and other things so that you can, and we are also leveraging with other than INCSys, and we are also leveraging the P&L resources that we have access to. So cyber data is coming from here because we model those, and then physical data is coming from here because we model those, and then we use the PingThings database. We use our own database, which is basically feeding the data to Resilient Grid tool, to INCSys Power Simulator, and then also to our tool, which is being developed at WSU, and the other two partner are Vanderbilt and University of California, Berkeley. So we have all these tools being integrated into the control room environment that I just showed. And we are modeling all the detail of cyber. We are modeling all the detail of physical system in dynamic simulation and dynamic interdependence analysis, because it's all real time. So it will be interdependence is a little bit easy because we are not using set of equation to model, but using dynamic simulators and real devices to be interfaced. So in interest of time, I'll quickly go to some results and then kind of summarize. But as you can see here, we have to model all these different server, so we can interface with INCSys HMI, we can interface with PingThing database, we can interface with EMS, which is from a Power Simulator, INCSys, and also we need a Splunk server where we can put all the cyber data. And this allows us to share with the P&L, where P&L can process it for the cyber detection. And we can process it here too with some cyber detection. And then, all these data, set of data should also be fed. So again, this is work which is going from like 1.5 year just to develop this test bed interface, and still kind of work in progress. We figured out that how to integrate everything, and we have finished a lot of these part, but it's not completed. This part has not been completed. Some are running in cloud, some are running in the lab. So let's talk about use cases and what we're looking at uh, in terms of different resiliency score and anomaly, and modeling some use cases for Ukraine or GridX. So here is the thing that we, in normal case, the way you'll see that you have a, basically all the firewall and everything switch and router model in the cyber network. Then we get all the information in the cyber log aggregator. And then we have this enterprise network, and we have this control network model, which already been completed. And then we have this substation network, which is in HyperSim and model, and exchange the data through NS3 with these. So cyber system is kind of these physical devices and model devices with the NS3, and then we have a physical system. And then we have a control room environment where these tools are being used. And we also have this cognitive science, using their own test, which is monitor the key human cognitive factor. So we will have a real operator, hopefully by next year when things are normal, coming to our lab and taking a decision for different kind of attack possible. And we will monitor their cognitive senses, using the same sensor that we just talked about later. And then also using monitoring the performance, that how they use the cyber and physical. And then we'll see that with the new tool, it's going to help them or it's not going to help them, right? So let's look at the scenario. So GridX is the one of those. There are different possibility. In fact, PNL help in bringing this GridX scenarios. So two of those is man in the middle, attack, and then another one is unauthorized remote login. And using this whole setup, we are very much set to model different kind of cyber attack, right? And this one comes from directly, which was helped GridX and NARC. So these are representative, kind of attack. And in the normal scenario, if you see that, that's where the attacker will be doing the man in the middle, right here at the switch that we model. And in this case, as we model this, then we still look at that what they can get access to, a set of data, what they can do the control, and how it will look to the control operator. The other use case that we did is Ukraine attack. And I know that some of you already know about Ukraine attack, that what happened, it evolved over several months, and close to like 18 months, one of the attack, where the started with the phishing email, then getting a privilege escalation in terms of access, and then finally from making a jump from IT to OT, and then finally opening the several different circuit breakers. It was not very well coordinated, so it does not resulted into blackout, but of course some brownout, and several customers went offline because of this relay opening, right? So if you do that in lab kind of environment, you send a bunch of email, and finally one of the user opens it, and then it gets infected, and then you send some setup. So for to get more information, scan the packet and all those kind of things. And because we had a real hardware relays, real hardware switches, so we can monitor those packets, and we can capture those traffic. And then finally, you can manipulate those. And the way we open it, I mean, of course, there are a lot of implementation is possible to do that. But the way we open is changing the relay setting file. Of course, you can do some other ways of opening the breaker. And then finally, you take control of circuit breaker because you have access to, you have privilege to access those set of machines. And then finally, control the relay to open a circuit breaker. And this is what happened. So this was done by one of my past student. or alumni. And you can now see that if you take a different action or different steps for a Ukraine attack, how resiliency will go down. So this one shows the cyber physical resiliency, and resiliency is going down by each step as it's being implemented. And if you can detect it early enough, you can take some proactive control to bring the system resiliency back and save the system. Here again, you can do it. But after after several step has been done, and this is very simplistic analysis because it was done for a small system, but after certain steps, there's not much chance to do that or bring the system resiliency back. So you have to be proactive in this case and take action. Right? And then some more test system for or test results for anomaly detection and root cause detection. So we applied it for several different cases. We are limited by our basically OPLRT system, that how large system we can model. So 179 was kind of maximum possible that we have, even though we can go for 300 system, but we cannot report the data out because we are limited on the not only by size but also on the data. And the other one is the Washington system, which is in progress. We are developing that Cascadia system. So the one that I'm presenting is a small system, so we can show some result. And also how do we measure that it's working well. So we have this recall, which looks at how many bad data we can detect and what are the actual bad data, because we are modeling it and we can inserting it. So these are level data. We can find out in actual system, you cannot do it because you don't have a level bad data in all the cases. So you cannot measure these kind of things. But here in the test bed, we can do it. And then precision is that we exactly detected all the bad data that was inserted. So we looked at performance of anomaly detector. It was pretty good, all in 90s, right? And the one thing that I did not talk about is recently we applied the Koopman based, which is a paper under review, which actually give us a better precision on recall because Koopman is designed for dynamic system. So it is better than statistical approaches and even machine learning. And that's data driven though, Koopman. In terms of event detection, we model the different kind of event. This is showing the partial list. All of those events were detected. You can sometimes you see no detection because the payload increase is under the threshold, which means that even if you do not detect it, it's okay because that payload increased by a very small percentage, and it was not. It was under the threshold of most of the detector that we have modeled. So even if you don't detect it, it's okay because the impact on the system is very less. This is about the PMNet, where we look at the dynamic system and with the concept drift. And as you can see from here, that accuracy, and this one is false negative rate and false positive rate. So those all come out to be very good, and it's kind of again in 90s. Here we are learning, so that's why there's learning time also shown here, and serial works out to be a little bit better. As you can see, optimal configuration is better. And this optimal configuration for DCDL, dynamic change detection is even better because you can detect and then change your threshold or a different thing that you use for detection of the concept drift. We also compared with different past technique from different references. And again, DCDL comes out to be a better technique, as you can see from all the different performance. So talking about the last thing, which is cyber resiliency. And if you remember the case that I talked about, different security mechanisms, you can do it with low or high. You can implement these different security mechanisms with the, again, these are only two categories. You can add more and more possibilities. And now I can compare that how my resiliency will change, right? So if I take a security strategy 2, this is how it's going to look like. If I take a security strategy 1, then this is how it will look like. And I can add more and more graph because once I have a tool, then just a matter of putting those data and getting the cyber resiliency, and then investing it right, which meets our economic expectation and highest resiliency possible. You can even optimize it with this. We also combine these two things together, that with anomaly detection, how your resiliency is changing, and without anomaly detection, how your resiliency is changing. Of course, as you expect, that if you can detect anomaly, my resiliency will be right, score. If I do not detect anomaly, then my resiliency score will be showing something which I should not paying attention to, because that's anomaly. Okay, so simple result like this. And then finally, let me just summarize as we are getting closer to the last part. First thing is that during extreme cyber event, situational awareness is very challenging, because our conventional differential and algebraic equation based analysis will most probably will not work. And then we need to utilize the data driven approaches while still not forgetting physics, because system information is available, whatever is available, it's very important to consider. So data analytics and power engineering should be integrated while applying the new data driven technique, which is of course much faster compared to solving a differential equation if you're doing the dynamic state estimation. And state estimation also has some limitation, and here also we have some limitation, but we can use those things together to find the best solution possible. And the key thing that we should emphasize is all about detection, classification, localization, and then prioritization, so that we can make it actionable information for the operator. They can look at that and know that what they can do to basically save the system or minimize the impact on the system. So decision support is very important, because everything that we are doing is all about taking a right decision. And we can also use the similar method for resiliency monitoring to take action and decision for planning, right? So it does not need to be only operation, because by comparing resiliency for different mechanisms, we can show that which one is the most economical, but still maximize the resiliency. A lot of training need to be done because operator is not familiar with a set of cyber data. And these tools are very important, that how it processes and shows the operator combined integrated information from cyber and power. And finally, we should not forget the cognitive science, because we are showing this set of data to operators. And the one thing that we are looking at is the dynamic attentional control framework to analyze with the cognitive flexibility and other things, and measure it with the actual set of operator to show these information best possible way. With that, I would like to thank, of course, IEEE Task Force on Cyber Physical Interdependence for Power System Operation Control to give me this opportunity to present my work, and NSF to fund this, and several different collaborators who are part of this large project. And more information is available on this website, and there is also a website that we have recently developed, is called resilientpowergrid.com .io. Sorry. With that, I'll be very happy to answer some question. I see there are a lot of questions in
Indeed.
chat. Yes.
Thank you, Anurag, for the presentation. It was a great presentation on the security and resiliency, and actually fits very well with the scope of the task force. There are many questions, as you mentioned in the chat. I will try to address some of them. I think if we're not able to address, I'm pretty sure we're not be able to address all of them, but I will post your contact details. And they have them here in this slide. People can follow up. So let me pick a few questions that I think would be interesting to address in the next 8-10 minutes. There is a question about the level of detail in regards with the modeling that you have done on NS3. So the question has to do is, what is the level of detail? Did you model directly protocols such as Goose, DMP3, Modbus, or you just model the communication topology and some communication network characteristics, not the protocols itself?
Yeah, so right now what we have done is DNP3. because that supports all our tools which we are using for different vendors.
Mhm.
That can be easily extended. I mean, in the past we have done Modbus and even Goose in the past, uh, but that was with RTDS, because RTDS has all these different kind of support for that, and it's all about how many we
Yeah.
can buy those translator. But yeah, this one, the one that we are developing, is with the NP3.
Okay. Okay. And I think actually because you mentioned RTDS, it fits well with the next question that has to do with if you can elaborate a little bit with the computational complexity and performance of the detection methods that you talk in terms of real-time applicability.
Yeah, yeah. So I did show you some time statics, which is showing in seconds, and and I think that's I mean, we can reduce it, but then we find that the performance is not very good. So in seconds we still call it real time, because SCADA report is we typically do like in every 2 seconds or 4 seconds, sometime in 10 seconds, depending upon which part of the country we're talking about and world we're talking about. But so this can perform in seconds, 2 seconds, and some approach like dynamic mode decomposition with which is our most recent paper, still under second review or third review cycle. That one can actually do it in millisecond.
Okay.
Yeah.
I think one interesting question that came actually right now, not so relevant with the presentation content itself, but a little bit related with what is happening and your work as well, is how your decision support tools and the research work that you have done might help control system operators uh, in events like the ones that happen in Texas, right? Not only about natural disasters, but if there was actually a cyber attack that could have been occur at the same time simultaneously with the actual loss of generation capability. So the question essentially is, when we have a physical or a natural disaster and we have at the same time a cyber attack, similar with natural events such as the one that we had in Texas, how your decision tools may have helped during these unfortunate events.
Yeah. Yeah. So I think everyone is thinking about that, how these tools can help. And I did not talk about my other tools. So I talk about CP-TRAM, which is Cyber Physical Transmission Resiliency Monitoring. But we do have other tools, which is all about monitoring the weather impact on the system. And a lot of work need to be done, because it's not an easy problem, right? So we are, I would say that certain percentage of what actually need to be done, and there are some steps towards that. But definitely analyzing the impact on of expected event, because this was expected event, and planning and analysis will definitely help. And we do have a tool called that, which is called Rtrms, real time resiliency management system, that we have developed. We worked with Alaska for that, and we customized that tool for their all the snow launch and tsunami and whatever can happen. uh, we need to find the event first, and we are extending that tool with several different other project. For example, working with Sierra City Light, working with Idaho Falls, working with Pacific Power and Corporation. So all of those tools, still a lot of work need to be done, but that RTRMS does exactly the same thing. That look at the expected weather event, analyze that what is the impact on the system, and then suggest some, for example, where to shed the load in a minimal possible way, so that the impact is minimal, right? Where to take out the line out, or anything like, which is something like California, which is against the wildfires. So there will be some outage, but that tool allows you to support the power to critical loads, where like airport, hospitals, and all those kind of things. And unfortunately, there's not a good solution. So if you have a limited resources, we cannot power everyone. But if you do a good planning analysis using that tool, and which can be enhanced more and more, it will be very much applicable and will definitely help.
Indeed, indeed. And as those, unfortunately, has become more normal, all those tools will also help for better planning and operation. So with that in mind, and with having the resiliency metric that you have developed that we talk about, I think CP-Trump, there is a question is about wouldn't be this resiliency metric more accurate if we consider the topology of the interdependent cyber and electrical networks instead of analyzing them separately and then combining them and then combining them for the resilience score. So the question has to do is if the analysis would be done better if we do that, if we analyze them together instead of separate and then combining those scores.
Yeah. Well, I think we can look at both the ways. The reason for keeping it separate was two. First, who's using it? So we know that we have a control room operator and we have a network operation center, and both need a separate set of information, right? So if I talk to a bunch of utilities, they do want it separate. Second, if something is happening, I need to tell exactly that why it is happening, right? So all the time, it's not a cyber factors which is impacting resiliency, but sometimes it's other factor, which is a physical system, which is more often actually, at least at this time, is impacting. So I can quickly find the root cause. Now this interdependent is already modeled because it's not reflecting resiliency score, but the interdependency is already modeled because it's coming from the interdependent system. And even in our model, the cyber network is reflecting everything because it's overlapped on the overlapped or very much dependent on the power grid network, right? So fundamentally, it's interdependent. The factor that we are processing in the end, it is just telling that if I see a correlation between cyber factors and physical factors, then I know that's a cyber physical, right? So, but again, that's not the only way to do.
Yes,
And the
yes.
reason was that, I mean, these keeping it separate came after talking with, I don't know, maybe like 30 different control room industry member that I talked to.
Maybe it's also an idea for expanding the work, right?
Yes.
So that is also a kind of purpose for research. So that was a good time at then, but now maybe also a comparison with a more, interdependent approach will be a good also to consider. So due to time constraints, I will ask only one last question. I'll try to combine two questions into one. It has to do a little bit with the comparison between model-based and model-free methods for anomaly detection or resiliency modeling. Can you elaborate a little bit on the benefits and drawbacks, since you have mentioned that sometimes we don't have enough data for data-driven approaches and sometimes they are not balanced. So one question has to do with comment on the comparison between them, and the other one has to do with wouldn't being GAN's generative adversarial networks helpful to generate more data for the database approaches?
Yeah, so that's a great question, and this is something that we have been thinking about, since we started this work almost 6 years before. And unfortunately, there's not a good answer, which means that there's no approach which is which will work on different things. So because we don't have available data, so we cannot do the training, and that's why we thought that unsupervised is better. Now, in supervised method, if you use this soft labeling, where you use a probabilistic approach, which is our newest work, which I did not talk about, but there's paper submitted. If you use that, then you can apply with very minimal labeling. You can still apply the machine learning approach, which is supervised, which is actually supervised is better in terms of accuracy because you train it in advance, and as long as you consider the dynamics and consider the concept drift, data drift, which I talked about, it will work well. Um, in terms of confidence on each of these methods, which is mainly like a regression, and those quickly goes very low. So as we add more and more data into which is a bad data or which is a bad event in the system or unexpected event, regression will go, accuracy will go down very soon, while supervised will go very slow, right? Because it's a train with a lot of data, and depending upon your training, that how you do it. And then state estimation, we all know that even with the 30% bad data, it starts to give a bad result. And we, 40 to 45% is kind of limit. After that, it will totally give you state, which is not the true state, right? So that's how estimation theory works in state estimation. If you make a dynamic state estimation, that's less robust, right? So dynamic state estimation is less robust because it's more complex maths. So complex is typically less robust, right? I mean, if you look at the system theory. Now, so considering all these things, some has advantage, some has disadvantage, and that's why we adopted ensemble. So ensemble approached, and then in the newest paper that we had, that we have to do a double check, and that's why I was saying that if you go from localization to the classification and then again back from classification to localization, that will be kind of double check, and you can solve these with supervised and unsupervised method, and then follow up with dynamic mode decomposition, which is a system theory driven, to double check. And if you find some anomalies, you at least you have to check with the third to tell the operator that, and that's why trust is also important, that anything that we report, we also tell the confidence factor on that. This is anomaly, but here is a 30% chances that I think, and this is an anomaly which I think 90% confidence.
Yeah, exactly. It's not everything black or white, benefits and drawbacks. And also that is why we have, as you mentioned, rise of ensemble or concurrent kind of approaches, model-based data-driven with confidence scores in order to provide a level of confidence in the overall outcome of an algorithm. With that, Anurag, I would like to thank you. I think from all the webinars in the task force, your presentation was a lot relevant with our scope of work. And I would like to thank you again for taking the time to talk. I will make also a joke here in your Blackboard in this slide. I see that Greek is missing from the thank you list. So maybe it's an idea to add it. And with that, I would like to thank everyone as well for joining. Dr. Srivastava contact details are here. I apologize for the questions that we're not able to answer, but I'm sure he would be happy to answer any questions if you can reach out. Again, thank you.
Thank you
for your time.
Harris, for the opportunity, and please feel free to reach out to me through email if I could not answer. And thanks for great questions here.
Thank you. Have a nice day or night, everyone. Bye-bye.
You too. Bye.